Imagine firing a Nerf pellet from a stationary position on the ground at 40 miles per hour. If your friend, moving in a car at 20 miles per hour, looked out their window, they would see your pellet traveling at 20 miles per hour, as opposed to the 40 miles per hour you arrived at. Now, replace that Nerf gun with a flashlight. If you emit photons from the ground at the speed of light, and your friend in a spaceship traveling at half the speed of light does the same, a curious problem arises. Einstein's theories were based off the premise that light was constant in all reference frames. That means that both your photons and your friends must be traveling at the speed of light. But if both sets of photons travel at the speed of light from the frame of reference of your friend who is already moving at half the speed of light, their photons would seem to move only at half the speed of light, contradicting Einstein's premise. While many may have accepted this issue and moved on, Einstein considered a revolutionary possibility. What if the speed of light was constant, but time itself was not? A simple thought experiment can help explain this. Imagine a light clock with two mirrors spaced 1 light second apart and a photon bouncing between them. Whenever the photon hits the mirror, 1 second ticks for the reference frame in which the light clock is situated. If you're stationary, the photon moves perfectly vertically between the mirrors at its maximum speed, c, taking exactly 1 second per bounce. However, for a friend in a spaceship moving at 50% the speed of light, the photon not only has to travel vertically to bounce against the mirrors, but it also must travel horizontally just to catch up with the ship. And since the maximum speed of a photon is c and the total distance it has to travel can be calculated using the Pythagorean theorem, we can derive a simple equation for time dilation. The concept of time dilation leads to many other fascinating phenomena. Imagine standing on a giant cosmic ruler with markings 1 light second apart, while your friend rockets forward at half the speed of light. From your perspective, the markings remain 1 light second apart, but for your friend, time dilation, which at the speed is approximately 1.154 seconds for them for every second you experience, causes them to perceive the distance quite differently. Instead of covering 1 marking every 2 seconds, they would perceive covering 1 marking in about 1.733 seconds. This creates the illusion that the ruler markings shrink in the direction of motion, a phenomenon known as length contraction. Time dilation isn't only limited to motion, it also occurs due to gravity. To illustrate this concept, we must first accept that photons can be affected by gravity. For the purposes of this video, I'm going to leave out the explanation of why this is and focus more on the specific concepts. So I'm going to leave it as a challenge to research and figure out. If photons are indeed affected by gravity, imagine putting a flashlight forward. The beam bends into an arc, with the inner side of the arc being shorter than the outer side. Since the beam hits the ground at the same time and the outer arc is longer than the inner arc, it might seem like outer photons are traveling faster than the inner photons, but they're not. This is explained by gravitational time dilation. Photons closer to the gravitational source, in this case the core of the Earth, experience more time dilation, meaning that they cover less distance in less time, maintaining the constant speed of light.